In this video, we are going to discuss the idea of graphing a system of equations. I want to start off just by pointing out that if you've never used this website, you really should try it out. It's desmos.com, Desmos.com. You can see it written here at the top and up here in the URL bar. It is free. There is an app you can download as well if you have a smartphone. And this is actually the same calculator that shows up on the GMAS, which is a standardized test that we have in Georgia. There is also reason to believe that this may be showing up on other standardized tests in the future, so it's a good idea to start familiarizing yourself with this platform. Also note that there's a little keyboard down here at the bottom that you can use to input everything that I'm about to type. I'm going to actually type it in, but I just wanted to show y'all that that keyboard's down there in the corner. So I want to start off by considering something that we've seen before, which is the graph of what I would call your typical linear equation. Typical because it's y equals, in this case I've selected y equals 2x plus 5. That is in slope-intercept form, y equals mx plus b. But rather than leaving it like this, I'm going to go ahead and write this in function notation since we have been learning about functions. And in algebra, it's a good idea to kind of get used to seeing this function notation. So notice here that f of x equals 2x plus 5 did not change the line at all. F of x has taken the place of y because f of x is the output of our function, and x is still acting as our variable that's paired with our slope, which is 2. So I've graphed this equation, y equals 2x plus 5, or in this case f of x equals 2x plus 5, and it is in fact a function. If I were to graph another function now on this same graph, let's say I pick g of x equals, and maybe I change this up a little bit and make it 1/2 x, and I'll make it plus 2. Well, now you see in purple, you have g of x, which is the function g of x. It's the function g. And you have the green line, which is the function f. So I have two different functions that are graphed on the same graph. And if I zoom in right here, you can see that there's this point where they intersect, specifically the point -2, 1. And what that means is if you insert -2 into either one of these functions, so f of -2 or g of -2, that would mean that you take -2, which again is your x value here, and you substitute it in, you will get 1 as your output for both functions. In other words, this single point is the solution for both of these functions, and that is in fact the solution to this system of equations. So all a system of equations is when we take more than one equation and we look at them together and we try to find the point or points that they have in common. At this point, if you are unable to graph a line on your own, I would certainly recommend using something like Desmos, keeping in mind that you really do need to learn how to graph a line because that's not going to be something that goes away in any of your high school math classes. In this case, we say that this system of equations has one solution. There are other scenarios that can appear. So take, for example, our purple line here. If I change its slope, so right now it has a slope of 1/2, whereas our green function f has a slope of 2. If I change this slope of 1/2 and make it the same, 2, well, now you see that the lines are side by side. And there's no obvious intersection here. That doesn't mean they don't intersect, because I need to zoom out and kind of make sure they're not intersecting somewhere else. If I start zooming out, it becomes pretty clear that these lines never intersect. In this case, we call these parallel lines because they had the same slope. And in fact, if this was our system of equations, f of x being 2x plus 5 and g of x being 2x plus 2, if they have the same slope, if both of your equations in a system of equations have the same slope, they have no solution because there's no point of intersection for them to have a solution. There is a third possible scenario that can occur. So just to recall, so far we talked about if the lines intersect, there's one solution. If they never intersect because they have the same slope, then there is no solution at all, because you have to intersect to actually have a solution. And the third case that can show up if you have a system of equations would be if somehow or another you manage to graph the same line more than once. Meaning you have two lines that perfectly overlap each other. And if you have two lines that perfectly overlap each other, basically what that's saying is there's not one point of intersection. There are infinitely many points of intersection because you literally have two of the same lines. To illustrate that, I need to rewrite this function with our y value. So we now have y equals 2x plus 5. Notice the actual line didn't change. And I'm going to change the way this equation looks. So just to kind of remind you, the rule for solving an equation is that you can manipulate numbers, variables on either side of the equation by using the order of operations, PEMDAS, backwards, and by using inverse operations. Well, an extension of that is this idea that the equal sign just tells you that this equation has to be in balance. So, hypothetically, you can do anything you want to, as far as an operation goes, to one side of the equation as long as you do it to the other side, and it will remain the same equation. So to illustrate this, if, for example, instead of y equals 2x plus 5, you had that same equation, but with every term multiplied by 2, let's look what happens. 2y equals 4x plus 10. Well, notice my green line's there, and my black line is also there. So I'm going to turn the black line off. There's the green line. Turn the black line on. It's the exact same line. And that's because if you look at this second equation here, you can see the 2y, the 4x, and the 10. If you divide all of those by 2, you wind up with the same exact equation as you started with above. There are other scenarios where this could occur. For example, you could have a situation where your slope is actually the same. It's just written out differently. So like instead of 2, you might have like, I don't know, let's say 10 over 5. Well, 10 divided by 5 is still just 2. So I've just written the same equation twice. It's just this second one is not fully simplified. In any case, if you wind up with the same equation, the same function, and you're asked to solve them as a system of equations, then they have infinitely many solutions because they intersect at every possible point into infinity.